Welcome to today's IBT ABC UTC research seminar. The presentations in these seminars highlight research work at the IBT ABC UTC's partner universities. Each seminar consists of a 40-minute presentation followed by a 15-minute question and answer session. The Q&A session will extend at most to 2:15 Eastern. My name is Kathy Kroll. I'm the co-director of technology transfer at the IBT ABC UTC. I'll be moderating today's seminar. I'm assisted by Don Diggeman, Georgia State Bridge Engineer, and Bijan Kaligi, another of our co-directors for the IBT ABC UTC focused on implementation. Don and Bijan will be moderating the question and answer. And Keitha Arvan, assistant professor at FIU, will be managing the web room. We're pleased to welcome participants at approximately 500 registered sites for today's seminar. Our featured research project today is pre-stress losses in UHPC and hybrid precast prestressed bridge girders. Our presenters are Omar Yadek and Royce Floyd. Before we get started, I have a few announcements regarding upcoming web events. The next quarterly research seminar is on Friday, April 25th, from 1 to 2:15 Eastern. The featured project will be Quantitative Condition Ratings, Quant-C-R, for Transformative Bridge Asset Management. It will be presented by our partners at the University of Georgia. Our next monthly webinar will be Thursday, February 20th from 1 to 2:15 Eastern. Our featured presentation will be on FastCast bridges for rural transportation solutions. Our presenters will be from the FastCast bridges. The monthly webinar in March will be on March 20th from 1 to 2:15. We'll be featuring sprayable UHPC on a project that VDOT did for an abutment repair. We'll also be discussing the development of mobile capability to really take that technology to anywhere. That brings us to today's presentation. Before I introduce our presenters, I will review some housekeeping items. Many of you may know these webinars are recorded and posted on the IBT ABC UTC website in the section titled Research Seminar Archives. So you can access this and all previous seminars for future learning and to share with interested colleagues. I'd also like to point out that a PDF version of today's presentation is provided in the Go-To dashboard on the right side of your screen. You can download these PDFs during the training session. They will also be posted in the archives. Lastly, this presentation will be followed by approximately 15 minutes of question and answer. Please enter any questions you have in the question box in the Go-To dashboard. The seminar today features the IBT ABC UTC research project on pre-stress losses in UHPC and hybrid precast prestressed bridge girders that was conducted at our partner university at the University of Oklahoma. We're pleased to introduce our presenters, Omar Yadek, a graduate research assistant in the School of Civil Engineering and Environmental Science, and Dr. Royce Floyd, who is the principal investigator and associate professor at Civil Engineering and Environmental Science, both at University of Oklahoma. Again, we welcome Omar and Royce. We'll now begin our presentation. Royce, we see your screen. We can't hear you yet.
Excellent. So good morning to everyone, or afternoon, depending on where you are. Thank you all for attending today to hear a little bit about our work. And as was mentioned, Omar and I are going to talk to you about our project on pre-stress losses in UHPC and hybrid precast pre-stressed bridge girders that was sponsored by the IBT ABC UTC. Omar has been working with me for about the last 4 years, and we've been working on several projects related to UHPC, including that he has been out on a couple of field projects in Oklahoma with me. I'd also like to acknowledge my co-PI on this project, Dr. Jeff Volz, and his contributions, as well as the contributions of his former students to this idea of composite UHPC and conventional concrete bridge girders. This presentation is going to consist of an introduction to the topic by me, followed by Omar taking over to discuss more details, including the literature review that was conducted, our research objectives and approach, as well as the actual methods we use to construct the specimens, results that were obtained from testing, and then our preliminary conclusions and ongoing work on this topic. So let's begin with the introduction. Most of you are probably familiar with the concept of accelerated bridge construction, evidenced by you being at this webinar, but our specific connection to ABC in this project is related to the use of prefabricated elements to accelerate construction of a bridge. Use of prefabricated elements and accelerated bridge construction in general allows for improved constructability on the site, which leads to better traffic flow and work zone safety by reducing the impact on traffic, as well as leading to a shortened project delivery time. Precast, prestressed bridge girders are a common prefabricated element across all kinds of bridge systems. And when compared to a regular reinforced concrete element, they're going to use less concrete and less reinforcement, potentially have a longer service life and less required maintenance due to reduced cracking, and then also to allow for longer spans, kind of again compared to conventional reinforced concrete. They're cast offsite in a precast yard using reusable forms, standard cross-section shapes, etc. And generally, they're going to be pre-tensioned, where the pre-stressing strands are tensioned between bulkheads before the concrete is cast, and then the pre-stressed is transferred by cutting the strands once sufficient concrete strength is achieved. There are a lot of design considerations that are interesting, specifically to pre-tensioned girders, and some of them have received a lot of attention over the years. Some that have been concerns of the Oklahoma DOT, as well as around the country, include the fact that the high forces and concentrated stresses in the end region of the girders can lead to potential cracking, affect the pre-stress transfer length, potentially open the girders to some durability issues. Additionally, pre-stress losses from immediate and time-dependent deformation play a key role in service and strength level behavior. And then shear demand is going to be high in the end region of the beams, and the shear capacity in that end region is going to be affected by the pre-stress and potentially is changing over time. This specific project was at least partly motivated by experiences in Oklahoma related to bridge deck joint deterioration, similar to what we show in these pictures, where damage is incurred to the joint armoring, which leads to failure of the joint sealant and allows water to pass through the joint and onto the beam ends. In fact, the first project that Oklahoma sponsored related to UHPC research was related to deteriorating bridge deck joints. So you might say, why does that matter for the pre-stressed girders? Well, the problem that we saw in Oklahoma specifically is that water leaking through the joints onto the ends of the pre-stressed concrete beams can lead to corrosion of the reinforcement, spalling of the concrete in the end region, which can impact the shear behavior and also the transfer of the pre-stress in the end region. Oklahoma has sponsored several projects on behavior of older bridge girders in their pre-stressed bridges, as well as methods for repair and rehabilitation of these end regions. And in light of the previously mentioned design concerns and exposure of these end regions, alternative methods for design and construction have a lot of potential to improve pre-stressed concrete beam performance. One of those possibilities is ultra high performance concrete, which is of course in the title of this presentation, or UHPC, which is an advanced cementitious composite material that has a very high strength in compression and tension, as well as high durability, and has a lot of potential for use in strategic areas of concern. It's commonly used for bridge deck panel and precast element connections, and has also been used for expansion joint rehabilitation and bridge deck overlays across the country. Originally for this project, ODOT had talked to me about doing some research related to full UHPC girders, but there's been substantial research out there conducted on full UHPC precast prestressed bridge girders, including work to develop innovative cross-sectional designs, mitigating high stresses at the ends, and then maximizing the properties of the UHPC material. However, this comes with a high cost. And so one of the possible solutions to the high cost of full UHPC bridge girders is a hybrid girder, where conventional concrete is used for most of the bridge or of the girder section, with UHPC only in the regions of high stress or high demands, such as the end regions, in this case, to save costs and efficiently use the material. However, it's very important that we get compatibility between the materials, that we have construction methods that can be used to actually make this happen, and then having an understanding of the overall behavior are all still things that need to be addressed, and this research works to answer some of those questions. And with that introduction, I'm going to go ahead and pass it off to Omar, who's going to give you some more details of the work that we have done specifically.
Thank you, Dr. Floyd, for passing it. So I'm going to start with talking about the literature review in this research study. Several research studies investigated the end region detailing for crack mitigation and stress limits. Starting with Ross's report presents the results of experimental and analytical investigations that were conducted to evaluate the effects of end region detailing for the strength and serviceability of bridge girders. They proposed models that can be used to design effective end region details based on experimental work. The experimental work that they did in this project included load tests of 32 pre-tensioned precast girder specimens, where those specimens were loaded in 3-point bending and ranged in size from 28 to 63 inches deep. Analytical work in this project utilized the finite element analysis method, where the FE models were linear elastic and were intended to use to model the behavior of the end region prior to cracking. As one potential application of UHPC, as Dr. Floyd mentioned, is UHPC precast prestressed concrete bridge girders. The Federal Highway Administration and the Precast Prestressed Concrete Institute, PCI, have been evaluating UHPC prestressed girders in shear, flexure, and bond. The high compressive and tensile strength of UHPC combined with the large diameter 0.7-inch pre-stressing strands has the potential to create long spans and exceptionally durable girders. In addition, due to the inclusion of the steel fibers in the UHPC matrix, it has the potential to reduce the required shear reinforcement and required only supplemental reinforcement to control bursting and transfer stresses in the end regions caused by the large pre-stressing forces needed for long span girders. Mohibi and Grable investigated long-term behavior of UHPC girders, where a finite element model was also created to match the data that they got. As full UHPC pre-stressed girders might be more expensive than conventional concrete, a few researchers studied the hybrid option, where basically UHPC and normal concrete were used together. Lee examined the flexural properties of composite prestressed UHPC normal concrete T-girders. The UHPC was placed in the tension region and the normal concrete in the compression region, as shown here in the figure on the right. They tested 10 large-scale composite prestressed girders and 1 normal concrete prestressed girder, along with an analytical model to simulate the flexural properties of those composite girders. As end region in prestress has been a concern, a different design of hybrid prestressed girders was evaluated by a research study conducted at the University of Oklahoma by Choate. The intent was to use the UHPC at end regions, and the rest of the girder would be just designed with normal concrete. This concept was similar to another research study done at the University of Florida, where they investigated hybrid UHPC SCC bridge girders, evaluated the performance of the UHPC end regions, and tested different interfaces between the SCC and the UHPC. Choate explored the concept of hybrid UHPC conventional concrete girders and evaluated the shear behavior of the end regions and the continuity across the interface between the two concretes. With proper interface methods and textures, the performance of the large-scale hybrid girders matched the monolithic UHPC members with added advantages resulting from the presence of UHPC in the end regions. Precast UHPC shells have been shown to be effective for use as stay-in-place formwork for bridge columns and other ABC elements, but no data was found on using this type of stay-in-place formwork for pre-stressed concrete elements. And the added component of the pre-stress, obviously force, complicates the composite behavior of these kind of hybrid beams. Precast, pre-stressed bridge girders are a key component of many bridge systems and ABC methods. Increased span lengths associated with UHPC girders and improved performance from hybrid UHPC conventional SEC girders have the potential to reduce the required number of spans on a given bridge, thereby shortening the required construction time and improving the overall durability of the bridge system. So here why some research has been conducted on some aspects of UHPC bridge girders dating back to the first decade on the 21st century. Limited research has been conducted on the long-term behavior of these girders, including pre-stress losses from creep and shrinkage. The design of the pre-stress girders requires a proper understanding of pre-stress losses to avoid service load cracking and durability concerns. So research by the Federal Highway Administration included detailed measurements and prediction of pre-stress losses for full UHPC girders, and others have reported lower overall pre-stress losses for those UHPC pre-stressed beams. Another research study by Amari and Alborn showed that thermal treatment on UHPC led to improving the properties of UHPC, including time-dependent behavior and potential reducing the pre-stress losses. However, little information was found on the pre-stress losses, but for the composite UHPC conventional concrete girders. So based on the literature review, this study has been conducted with three main objectives. The first one is to measure the pre-stress losses for half-scale AASHTO Type 2 UHPC pre-stressed bridge girders. The second is to investigate the effect of a hybrid UHPC conventional concrete girder design on pre-stress loss behavior. And the third is to evaluate the effectiveness of different design details for mitigating stresses in the girder end region and their effect on hybrid girder capacity. So starting with the design, so in terms of the design approach, 10 approximately half-scale AASHTO Type 2 pre-stressed girders and 2 UHPC stay-in-place formwork shell girders were designed, and 8 have been constructed at the Structural Engineering Laboratory at the University of Oklahoma so far. The girder specimens were designed to utilize the existing formwork that we have at OU and stay within the constraints of the OU pre-stressing bed that we have, and to obtain the required stress state to match with the previous work done by Choate. The length of the hybrid girders was chosen to be 18 foot long to match the existing formwork, and in the figures on the right here, you can see the existing formwork that was used and the cross-section of that formwork. Allowable and concrete stresses at end regions and midspan were calculating following AASHTO LRFD bridge design specifications for both pre-stressing stress of 180 KSI and 202.5 KSI. The tensile, compressive, and allowable stresses of the pre-stressed girders at end regions are presented in these figures using the conventional concrete compressive strength of 7,400 PSI at release. In both pre-stressing stress cases, the compressive stress did not exceed the allowable. However, when we talk about the tensile stress, it did exceed the allowable stress. So top steel reinforcement was actually added to accommodate that high tensile stress in the hybrid and the conventional concrete beams that we did. In terms of the mix designs that we used for the concretes, J3 UHPC mix design developed at the University of Oklahoma through funding by the Oklahoma Department of Transportation and ABC UTC was used in this study for the UHPC portion. The table here on the right shows the composition of J3 UHPC with a 2% steel fiber content by volume. The mix design on the left was used for casting the self-consolidating concrete, the SCC, portion of the girder specimens with an expected 28-day strength of 10,000 psi. A high-range water-reducing admixture was used and added to achieve the desired slump flow that we need for our SCC mix, and the targeted slump that we needed for all the specimens was between 25 to 27 inches. The design of the hybrid beams was based on a previous study done at OU by Choate. One end of the hybrid UHPC prestressed girders was designed with the UHPC, as discussed, and the rest was designed with SCC. In this way, we were actually able to compare between the SCC and the UHPC end regions for each of those hybrid beams. All the girders were designed to obtain a shear failure to evaluate shear strength of the girder end regions and to investigate the effectiveness of those composite behavior of the UHPC SCC hybrid sections. These tests will be conducted after the prestress losses have stopped changing significantly, so we haven't done those tests yet. And in order to obtain the shear failure, we reduced the web section of the UHPC end region, resulting in a different cross section as shown in the section BB here in the bottom right figure. As continuity in composite members is important, the bifluid interface was chosen between the UHPC and the SCC concretes due to its excellent results and continuity based on Choate results. And the bifluid means that both concretes, the SCC and the UHPC, were cast at the same time, which also simplified the construction process. For the full UHPC prestressed girder design, no shear reinforcement was added or top steel to offset the high tension stresses, and only bursting reinforcement was added at both ends based on AASHTO section 5.9.4.4. The web was also reduced in these girders similar to the hybrid beams, and that can be seen here from the section BB on the right figure in the bottom as well. The girder length was also changed from 18 feet to 14 feet to reduce the amount of material required, since it was anticipated that the UHPC would actually lead to shorter prestress transfer and development lengths. 2 UHPC girders have been constructed at this point, but there are still 2 full UHPC prestressed girders to be constructed at higher prestressing stress with different end region detailing. For the stay-in-place formwork prestressed girders, the cross section was changed to be a 9-inch by 6-inch rectangular section, as shown in section AA on the bottom figure on the right, to simplify the form construction for this proof of concept. The dimensions were selected to match the applied stresses of the other beam specimens with the same number of strands and locations. The length of this type of a girder is 14 feet, not 18 feet, similar to the UHPC girders. The design has been finalized, but we haven't started with the construction of these specimens at this point, and it's still undergoing. Here's the parameter matrix for the specimens that have been cast already. So far we have 5 hybrid, 1 SCC, and 2 UHPC girders that were cast to evaluate the prestress losses. 3 main parameters were investigated. The first one was the length of the UHPC portion at the end region, whether it was 3 feet or 5 feet. The second one was the stressing stress on the girders, whether it was 180 KSI or 202.5 KSI. And the third one is the type of the concrete used. In addition, 2 different fiber contents were examined for the full UHPC girders, and that was mainly to investigate their shear behavior after shear testing. So now let's talk about the construction of those specimens, starting with the hybrid girders, since it's the most interesting one, I guess. So one side of the formwork on the pre-stressing bed with the web insert in place, whether it was the 3 feet or the 5 feet, were placed, and you can see those from the figure on the left. Then the reinforcement was set in place, as you can see from the figures on the right. The pictures here on the left show a close-up of the UHPC end regions. The top picture is for the 5-foot web insert, and the one in the bottom is with the 3-foot web insert. The 2 specimens were cast at the same time, and the picture on the right here would show you the layout of the 2 specimens on the pre-stressing bed at OU. After we did that, 3 vibrating wire strain gauges were used and placed at 3 locations. 1 foot from the live end, and here I'm going to start referring to the live end as the end near where the tension was applied. And then the second vibrating wire strain gauge was placed at midspan, and the last one was at 1 foot from the dead end, which is the other end. They were all placed on the top 2 strands and attached them to them using zip ties. After placing the instruments, the other side of the formwork and the end plates were placed, then a divider was inserted at the interface between the SCC and the UHPC. And this divider, you can see it from the figure on the left at the very end. And this divider was actually used to help control the flow of the two concretes when casting them. This divider did not block the entire width of the bottom flange, but did block most of the top flange and the whip widths. These pictures show the casting process of the two concrete mixes. Both SCC and the UHPC concretes were cast simultaneously as we were trying to achieve the bifluid interface. So we started mixing the SCC first before mixing the UHPC. Then we started casting some of the SCC first from the end opposite to the UHPC, since a larger portion of the girder was designed with SCC, self-consolidating concrete. And to make this casting process a little bit easier and to get a better interface between the two concretes, a couple of people were actually casting the SCC while some other people were at the UHPC end waiting to see the SCC starting to flow close to the interface. And then when the moment that happened, we started pouring UHPC using 5-gallon buckets filled with UHPC. Then visual observations throughout the cast were made to control the flow of each mix and to maintain equal heights of both materials while casting. The divider at the interface helped to control the flow rate of both mixes. The divider then was removed after we finished casting all the way to the top of the girder, and you can see the picture on the right here. It will show the interface after the divider was removed. And then the picture on the left here shows the complete specimen after pre-stress release. And pre-stress release was done 2 days after casting. Here you can see that there has been some SCC flowing into the UHPC end in the bottom flange, and this was the first set of the beams. So we're still trying to evaluate and to control the flow rate of the SCC to get a better interface between those two concretes. Moving on to the UHPC pre-stressed specimens. So those were all full UHPC specimens. The construction and the instrumentation for them were similar to the hybrid girders. No shear reinforcement was added, but only bursting reinforcement was added to the ends as shown in the bottom figure on the left. And again, these specimens were 14 foot long instead of 18 feet. Here is a few pictures starting from the left showing the UHPC placement, the reduced web section at the live end region, and the complete UHPC girder specimen. So the stay-in-place formwork girders were still not yet cast, but before we finalized the design, we actually did trial specimens. Those trial specimens were done to evaluate the bonding between the UHPC and the SCC concretes. 2 interfaces were chosen for these trial specimens, the smooth and the grooved inserts. And the reason why we wanted to investigate the bonding was that the UHPC was casted first, and then the pre-stress will have to transfer from the SCC infill into the UHPC formwork shell by bond between the materials. The order of which concrete is cast first is important, as usually UHPC is the concrete that is cast on the conventional concrete, not the other way around. Here, foam inserts and MOR formwork were used to create the UHPC shell. And the UHPC shell that was designed is to be a 1 inch thick. And here are the pictures showing the foam inserts for both interfaces inside the formwork. And the picture on the right shows the shell after UHPC was cast and the formwork was removed. Here are just pictures to show the complete trial specimen showing the end view of the UHPC shell after the SCC was cast. And moving on to the results. So in terms of the results, we're going to start discussing the results from the concrete shell trial specimens. 4-point flexure testing was conducted on those 2 specimens to evaluate the flexure strength for the composite element. As can be seen from the picture on the left, a vertical flexure crack occurred at midspan of the specimen, showing a good behavior and bonding between those two different concretes, the UHPC and the SCC. The bonding was excellent as we could not see any significant separation between the UHPC and the SCC, even after we completely filled the specimens to see the cross-section regardless of the interface, whether it was grooved or smooth. In terms of modulus of rupture, both trial specimens exceeded the SCC modulus of ruptures. You can see from the figure on the bottom here that the measured MOR from both specimens were more than double compared to the calculated MOR for the SCC. The grooving in the shell did achieve a higher failure load, but with only two specimens, we can make a solid conclusion that they both exceeded the expected strength for the composite specimen. Before we start talking about the results for the compressive stresses, here is the compressive strength for all the girders at release and at 28 days. The SCC averaged around 7,400 psi at release and 9,500 psi at 28 days, where the UHPC averaged 10,000 psi at release and 18,500 psi at 28 days in terms of compressive strength. So here the figure on the right shows the compressive stresses determined from the measured strain at both ends of the pre-stressed girders and the SCC allowable stress based on AASHTO LRFD at release. At each UHPC end, the measured stress was calculated using the measured strain from the vibrating wire strain gauge and the modulus of elasticity of UHPC that was proposed by Russell and Graybill. Similarly, the measured stress at each end of the SCC was obtained from the measured strain and modulus of elasticity determined by AASHTO LRFD. All the measured stresses were within the stress limit determined by the SCC. However, the UHPC ends exhibited higher compressive stresses than the SCC ends, which that indicates that the UHPC pre-stress transfer length is indeed shorter compared to the conventional concrete. In terms of immediate losses at midspan, the figure on the right shows the measured immediate elastic shortening losses compared to the calculated losses according to AASHTO refined method. The elastic shortening was calculated from the measured strain obtained after pre-stress release, which was again done after 2 days after casting. In all the specimens, as can be seen from the figure here, the calculated elastic shortening was less than the measured pre-stress losses, except for hybrid 2, where the losses were similar to the calculated value. Hybrid 3, 4, 5, and the SCC obtained similar immediate pre-stress losses, but in order to understand the behavior of the pre-stressing stress transfer along the girder, this graph would show the end regions and midspan elastic shortening for all the beams. All the hybrid beams followed the same trend. The UHPC end region and midspan had similar elastic shortening losses, where the SCC end region had a lower value. The values of the elastic shortening correspond to the high compressive stress and strain at the UHPC end regions and the lower compressive stress and strain at the SCC end regions, which is related to the location of the strain gauge relative to the transfer length. The two UHPC girders had a different trend than the hybrid girders. Both girders demonstrated similar elastic shortening at the live end, midspan, and the dead end, suggesting that the compressive forces were high along the entire length of the girder. Meanwhile, when it comes to the SCC girder exhibited lower elastic shortening at the end regions compared to all other girders. This indicates the lower compressive strains measured from the end regions aligning with the lower compressive forces at the gauge locations within the transfer length. Moving on to talk about time-dependent losses. The figure on the right shows the measured and calculated time-dependent losses at 35 days after pre-stress release at midspan. The measured pre-stress losses all exceeded the calculated value obtained from AASHTO refined method. The measured pre-stress losses of the hybrid girders at midspan were similar to the SCC girder losses. That suggests that similar behavior in the pre-stress losses between the hybrid and the full SCC girders for the time-dependent losses. The behavior of the long-term losses at end regions were similar to the behavior of the immediate losses at end regions for all the girders. From the figure here on the right, the hybrid girders UHPC end region and midspan exhibited similar time-dependent prestress losses. Again, this is an indication that the shorter transfer length that the UHPC has compared to the conventional concrete. So to evaluate the overall behavior of the prestress losses, we compared the overall prestress losses at the live end region and midspan between hybrid UHPC SEC1, which I'm going to refer to it as hybrid 1, and the full SEC girder. Both girders were prestressed to 180 KSI, and the hybrid girder, hybrid 1, had a 5-foot reduced width UHPC section. The figure on the left here shows the measured prestress losses over time for hybrid 1, or the UHPC SEC1, and SEC girders at the UHPC end region. Since UHPC has a shorter transfer length, putting the end region under greater stress. The black curve shows the greater deformation and losses over time compared to the SEC live end, where it suggests the high compressive stress resulted in more creep over time. As can be seen from the figure on the right, in the first 20 days after prestress release, the losses rapidly increased in the hybrid beam corresponding to the UHPC end region high compressive stress transfer. On the other hand, at midspan, the SEC was gradually reaching the losses of the hybrid girder after approximately 60 days of prestress release, and this could be an indication of different rates of creep development in the SEC. These figures present the comparison between the hybrid 1 and the UHPC girders, where both girders were prestressed to 180 KSI, and they both had the same 5-foot reduced web section. Here we can see that both girders had similar trend in terms of prestress losses over time at the live end region and midspan. The losses over time for both girders were similar at their live end region and midspan. However, the UHPC losses at midspan were higher over the first 20 days, and that's due to the higher compressive force transferred from the live end to midspan. This also could be due to the cracking that we actually observed on the top flange of the UHPC girders at multiple locations, reducing the moment of inertia. In this comparison, hybrid 1 was prestressed to 180 KSI, where hybrid 3, or the UHPC SEC3, was prestressed to 102.5 KSI. The figure on the left presents the measured prestress losses over time for both girders. Unexpectedly, the midspan losses over time for hybrid 3, which had a higher prestressing stress, was less than hybrid 1, even though more prestressing stress was applied. However, the trend in general was similar, where the prestress losses of the dead end region for both girders were less than midspan. But more investigation will be required in order to fully understand the behavior of those two specimens, where the next set of full UHPC girders will be prestressed to 102.5 KSI, which will help us to observe the difference in prestress losses behavior between full UHPC and hybrid girders for the 202.5 prestressing stress. In terms of conclusions, so those are the preliminary conclusions that we achieved from this study so far. The stay-in-place trial specimens showed good bonding between UHPC and SEC for both interface conditions. The placement of the hybrid prestressed girders with bifluid interface was successful for all the specimens. The UHPC end regions for all the hybrid prestressed girders followed the same trend, achieving higher stress compared to the SEC end regions. The midspan behavior of the hybrid prestressed girders was similar to that of the SEC prestressed girders, and the length of the UHPC section in the hybrid prestressed girders, whether it was 3 or 5, did not appear to have an effect on the prestress loss behavior at midspan for those tested. So some of the future work that we are going to have for this research study. So the formwork of the UHPC concrete shells are still currently under construction. Hopefully we'll be casting them in the next 2 weeks. 2 girder specimens will be cast with different interfaces between the UHPC and the SEC. 2 full UHPC girders with 202.5 KSI pre-stressing stress will be constructed to investigate the pre-stress losses with higher pre-stressing stress and to evaluate the different end regions detailing in the UHPC girders. Dig placement will be done also on all these girders. Then they will be tested in shear to evaluate the performance and the continuity of the composite girders. The shear testing will be conducted after we take all the required time-dependent pre-stress losses measurements that we need. And with that, those are the references that we use in this research study. And thank you all for listening. And with that, I would like to open for any questions.
Thank you, Omar. Thank you, Royce, for that very informative webinar. So we've got some questions here to start you off with, and I'll start off here with, please discuss how to reduce stress loss and what are the permissible loss ratios for pre-stressed concrete.
Omar, you want to take that or you want me to do it?
You can do it. I'll give you the first one.
Okay, that's fair. So, a lot of the ways that we're going to be able to reduce pre-stress losses are going to be similar across the board for pre-stressed concrete, whether that's going to be, reducing creep and shrinkage with different materials or being able to increase the stiffness to reduce the elastic shortening. In this project, we were focused more on understanding the impacts than trying to reduce them. But we do have some other students that are working on kind of a similar hybrid idea using concrete with less shrinkage and potentially creep for the conventional concrete section. In terms of the kind of allowable losses, that's going to be somewhat dependent on the design and what final stress is needed to meet the design requirements.
Thanks, Royce. Next question. Usually, pre-stress losses affect the possible sag in the beam, not so much the end stresses. Did you develop equations for a possible sag in the beam?
So we haven't actually gotten to that point yet. So changing the anchorage at the ends may impact this a little bit, but we anticipate that the hybrid beams to behave similarly to the conventional concrete beams. But so far, we haven't gotten to the point where we'd be able to develop equations for that possible sag.
Okay. And in that same vein, the next question, camber is traditionally difficult to predict accurately. Does this change better, worse, or same with UHPC or hybrid girders?
So kind of going off on what Omar said previously, it's also very hard to measure camber, and we haven't really done that. We think it's going to be similar in terms of behavior because so much of the design is controlled by the conventional concrete in these kind of hybrid sections, and so we want to try to get a reasonably accurate understanding of the individual materials and how they're going to behave together. Some kind of interesting things that we have seen that could impact these behaviors are with that force being anchored closer to the end, even though it's not that much, different. You are starting to get the pre-stressing force fully into the beam close or farther away from where you're getting, offset from the dead load. And so we did, potentially see some problems with additional induced cracking that has to be addressed. And then, these specimens, we only had one end with UHPC, so we could compare the two, and potentially having both ends be the same may give us a more uniform behavior and change our observations a little bit.
Next question, can pre-stressing in UHPC pre-tension girder be released after about 15 hours without large elastic shortening losses?
So that's a good question. some of that's going to be dependent on the specific mix design that's used and whether or not it can achieve the strength in that amount of time. To my knowledge, there are some out there that can get to the compressive strength in that time frame. Ours would take, some additional heat treatment and some other things to potentially get there. We haven't done much on modulus testing at those early ages to see if that, correlates well with compressive strength. But, my opinion would be that if we're able to get to, the same compressive strength that we are releasing at right now, so in this case, we were at about 10,000 PSI on the UHPC, that we would see similar behavior. And so it really is going to be dependent on whether the mix design can get to those properties in that time frame.
All right. Does this research include loss effects with different diameter steel strands and loss effects for carbon fiber strands?
So we haven't actually examined either of these items at this time in this research, but I think there would be good ideas, especially for the different diameter steel strands if we're going with larger diameters. But in this research till now, we actually haven't tested either of those different strands.
Okay, very good. Please discuss in detail how you will account for autogenous shrinking.
I guess you want me to take that one, Omar. So that's also a good question, and can be, a big deal, especially in the hybrid beams. And thinking about having these two materials together that are going to shrink differently, and the large autogenous shrinkage that we get with UHPC that's going to happen before we even release the pre-stress. In this, and what was presented today, we're only looking at behavior after the pre-stress is released. And so we're still looking into the data that we have from before pre-stress release to kind of see how that's going to impact the behavior of the beam, whether that's bond between the strands and the beam, or the beam pulling on the strands before we release the pre-stress, and then the behavior between the two different materials within the composite section. We have some planned testing to look at some of that, especially for the concretes that don't behave like or aren't traditional Portland cement concrete. But a lot of that is still ongoing. So it's kind of like we have gotten the after, or at least at this point, after pre-stress release, where a lot of that autogenous shrinkage is already going to have occurred, but we're still looking into what impacts that it may have for these hybrid sections.
All right, and I've got one more question, and I'll switch off to Bijan here. What issues did you have trying to design a scaled girder section?
So the potential issues with that would be the construction and the casting of those specimens, especially for the hybrid ones, where controlling the flow rate between the SCC or the conventional concrete with the UHPC could be a little bit critical, because in some of the beams that we actually cast, some of them, the SCC actually went into the UHPC end, especially from the bottom flange. So that could be due to the not really knowing the behavior at the beginning when we started casting those hybrid beams. But I think controlling the flow rate would be, the flow rate would be one of the major issues whenever we're going to, the full hybrid UHPC girders. I know, Dr. Floyd, if you want to add anything.
Well, I would just say on the design side, we tried to match stress states within the beam to go from the larger sections down to the smaller specimens, which is difficult to do in general. And, we didn't scale the strand size, but we did go with a smaller pre-stressing strand, which kind of goes back to that previous question that was asked about what's going to happen if we go to a larger strand. So say, we looked at 1/2 inch on this research. What if we go to a 0.6 or a 0.7 inch and it induces different kind of localized stresses in the beam? And so we were, for this research, more focused on the global behavior. And so we're trying to match, the applied compression and tension stresses in the beam to the larger specimen rather than, scaling down all the individual pieces.
All right, so hand it off to Bijan. Bijan, are you there?
Okay, yeah. Do you hear me?
Yes, sir.
Okay. Thank you very much, Ross and Omar. Great presentation. I continue with the list of the questions that we have, and then we go the two that we got in the chat box. So the next question, do you think it is possible for a production facility to adequately control the flow rate for placing the two concrete materials?
So I could take a start, Omar. You can talk too. It is a concern of trying to get the materials placed at a similar flow rate, and we've spent a fair amount of time trying to figure out ways that could be improved or modeled better, et cetera. One of the things that I often talk about is if our graduate students can do it in the lab, it should be scalable to folks that know more than we do. And so, if adequate planning is done ahead of time, it should be possible to be able to scale that up to larger production.
Thank you. Next question, does using different length for UHPC and hybrid specimen have an impact on the result?
So I kind of mentioned it previously during the presentation. So it could be said, but then the fact that the UHPC had a shorter transfer length, so reducing the length from 18 to the 14 to the 14 feet long beams did not really have a big impact, especially that the UHPC has the shorter transfer length comparing to the conventional concrete. So I think that's one of the main reasons why we wanted to go from 18 to 14 is because this material can be eliminated without having any comparable issues between the hybrid and the UHPC.
Okay, thank you. Next one, did you see any consequences of not including shear reinforcement and top steel in the full UHPC specimens?
Yeah, so after we actually demolding and we did the pre-stress release, we started seeing some vertical cracks on the top flange of the UHPC of the two UHPC beams. We actually saw them at multiple locations, and even though there was fibers, but then that did not really help in controlling to avoid these cracks because of the pre-stress. And since it was kind of wanted to evaluate that because we knew that the tensile stress at the top will actually exceed the allowable stress. However, we still went with that to see if there's going to be any potential issue, and we did see those vertical cracks due to that tension.
Okay, that was a list of questions that we had pre-webinar. Now we go to a question during the webinar. As I have one question over there. However, both types of concrete cast while controlling where the transition occurred.
So that's a good question, and like we've kind of mentioned a few times, it takes some practice to get the two controlled. We have a very flowable SCC conventional concrete, and then the UHPC is also very flowable, and will flow out of any gaps that you can find anywhere. And so we went with recommendations from some of the previous work that's been done at OU, at Florida, and elsewhere of kind of having a divider that helps to kind of set that location and also to provide some separation at the beginning. And so it's only a portion of the width across the beam, but it kind of gives us the reference point of where we want the interface to be. And then having, two different people controlling the material placement with another person kind of observing, to be able to say that, the SCC is, gaining, a specific height within the beam. We need more or faster UHPC placement to match that, and just trying to maintain that as we went up throughout the beam. And Omar, showed a picture that I think I still am sharing slides, right? So let me go back to this picture that he showed, kind of the first beam that we cast, where you can see that the interface was intended to be here in this location, but we actually ended up with more SCC being placed or flowing into the UHPC section than what was anticipated. And that was, part of the learning curve for all of us as we were making these placements. And then on our, subsequently cast beams, we didn't see that as much because we were better able to control those flow rates to keep everything the same. There's also the possibility for different densities between the materials, and so one is pushing harder on the other. And we've even talked with some of our chemical engineering colleagues about how we might be able to model that fluid flow to better, quantify these flow rates. But it is something that takes some work to get right.
I mean, just adding to that, you can see from the other beam, so the other beam we actually casted after we cast the first one, and you can see that the SEC did not really flow as much to the HPC end region like the one we see.
Okay, I think you guys are doing great in answering questions. There's one in the chat that was you're okay, we can go through that. And the question is, did the research include a mechanical device embedded in the UHPC shell? This is part one of the question, and part two, if not, please comment on the ability of the hybrid section to behave as a composite.
So I could take a start, Omar. So on the UHPC shell trial specimens that we did, one specimen was just completely smooth on the inside. There was no mechanical anchorage. There was no what's the word? There was no inside texture other than you sandblasted those, right, Omar?
We actually didn't, because I mean, you can go back to the concrete shell to show those mechanical anchors if you want, Doc.
Yeah, so the second specimen that we cast did have grooves that were formed into the side, so you can kind of see them in the foam here. And then over here on the right, on the completed shell, you can see the ridges in the UHPC that were formed along the sides and the bottom of the specimen. But in this other one, it was smooth on both sides. And so we didn't have any kind of mechanical connections on those. And so when we went to the finished specimen, you can see kind of that interface around the shell. But then when we went and did the testing, we didn't see any movement between those individual materials. Now, for the hybrid specimens that we've constructed up to this point, those were a vertical interface rather than having the horizontal interface. And those were cast with both concretes being fresh. Our previous student, so Jake Choate, a couple of years ago, looked at both doing this where we cast both specimens simultaneously, as well as casting either the conventional concrete first or the UHPC first, and forming a mechanical texture on the interfacing surfaces, and actually found that the bifluid process, he called it, of casting them at the same time actually gave the best result and was the easiest to do. Now for the UHPC shell specimens that are going to be pre-stressed, we're going to have to examine some different potential mechanisms between those two pieces to ensure that we get load transfer between the two. And unfortunately, we haven't gotten all that done yet.
Okay. Another question came up on what we are showing. Does these groups provide composite action or consider for composite action?
So in terms of what we've done so far, we believe so. The specimens failed due to a single flexural crack propagating all the way through the specimens with no indication of slip between the two, and that's kind of where Omar hedged on his conclusion from this, because we have a limited number of specimens that we've tested, and so it is uncertain whether it is going to give us true composite action, but please stay tuned and hopefully we'll have some additional results to present soon.
And I think because we're going to scale it up. So those were 8x8 specimens, and we're doing a 9x16 pre-stressed specimens. So obviously those things will add more complexity and complications to the bigger specimens. But that's why we still want to try to evaluate one that is smooth and the other one with some mechanical anchorages to see if it's going to make a big difference in the big specimens, or it's going to be similar behavior than those two trial specimens.
Okay, one last question, I promise. This is the last one. So the picture that you showed from UHPC SCC interface, after casting, did you see any gap between them?
No. You want to go back to the picture, Dr. Floyd?
Yeah, I'm trying to get back to it. This one, right?
Yeah.
We did not find any gap between those two materials. The interface was pretty much all like kind of got into each other because they were both still fresh, and whenever the interface was done, the concrete was still fresh. So we did not see any gaps in any of those 5 hybrid beams. That's why we decided to go with the bifluid interface instead of the other interfaces, because whenever there was if the SCC was cast first and then we're trying to cast the UHPC, there might be some potential separations or gaps that you can see. But in the bifluid, we did not really see any gaps in these specimens and even in the previous study as well.
Yeah, I mean, one concern, that we kind of mentioned at the beginning is, with these potentially having differential shrinkage behavior or different shrinkage behavior, there's the possibility for that kind of a gap to open up, but we didn't see that on any of these specimens. And then once we pre-stressed them, obviously we're putting a compression across that interface, but we didn't see a gap even before we pre-stressed them.
Okay, gentlemen, that was the list of questions I had. I hope I didn't miss anything, Kathy. Otherwise, I turn it back to you. Thank you very much.
Sounds great. So thank you again to Royce and Omar for sharing your IBT, ABC, UTC research work and for your thoughtful responses to the question and answers. Thank you also to Don and Bijan for moderating the Q&A session, and to Ankita for managing the web room, and to all of the participants for your interest, attendance, and questions. Our next quarterly research seminar will be on Friday, April 25th. Please join us then. This concludes today's seminar. Thank you all.